Oh, well, thank you. Yeah, so a big thank you to Soumitro and the other organisers for inviting me to be here today. So I've been asked to speak to you about piecewise-smooth differential equations. And such equations model systems with impacts and switches and any sort of discontinuity. And piecewise-smooth systems exhibit often very different dynamics to smooth systems. And in fact, I think this is quite a what do I want to say? Well, at the moment, it's quite an active area of research, and so as evidence of this, so here are 4 recent articles from SIAM Review. So SIAM, if you don't know, is the Society for Industrial and Applied Mathematics, and SIAM Review is their flagship journal. It covers all of applied maths. They just have 20 to 30 articles per year, and quite remarkably, since beginning of 2016, 4 of these have been on the dynamics and bifurcations of piecewise-smooth systems. So perhaps I'm biased because one of these papers is mine, but I think this goes a long way to show that that piecewise-smooth systems is currently a very active area of research where progress is continually being made. Okay, so I've written some lecture notes for you. I'm hoping they'll get that. In fact, they should be on the school webpage, but I'm hoping they'll get printed today, and so you'll have a paper copy. So in these lecture notes, these are the sections. So over the next few days, you'll have me for 6 lectures and a couple of tutorials. Yeah, so I have to start with an apology today. Is that today I'm just going to cover smooth systems. I just want everyone to get on the same page. So much of this might be a review for you, but I'm confident that there'll be something here today that will be new for everyone. But feel free to interrupt with questions as we go along, and I'll use the blackboard quite a bit. Please stop me if you think I've done something silly on the blackboard. I'm still a bit jet lagged from my travels. Yeah. Perhaps I'll start over here. Okay, so just want to start with linear systems. So linear systems are rather boring, but over the next few days, a lot of what we'll look at is piecewise linear systems. So to understand piecewise linear systems, we really need to have a very good understanding of linear systems. Okay, so here's what I think of as a linear system. So this is an n-dimensional linear system. Yeah. Yeah, so X is an n-dimensional vector. A is an n by n matrix. N by n. It's made up of real values. And so the dot represents differentiation with respect to time. So this is an ordinary differential equation. So in my lectures, we'll be looking at ordinary differential equations, whereas in most of the other lectures, I believe you'll spend most of your time looking at maps. Okay. Let's try a different color. Let's see, orange. So an example of a linear system. So a mass on a spring. And we'll do U. U is what do I want? 0. Okay, so this is an equation you've probably encountered before. So U here U represents the displacement of a mass on a spring. M is represents the mass of the mass, or block perhaps. B is the damping coefficient, and K is the spring constant. So you'll notice it's not in the form that I've written up here. So to rewrite it in this form, I'll introduce a second variable, V. I'll let V be the velocity. And then what? So V dot is U double dot plus V plus K U V dot minus K M Okay, so we've got V dot, and we've also got U dot as V, and U dot V. So I'll let X be the vector UV, and let UV. And so then I have X dot X. And so then I'll have a matrix. So U dot is V. So I've got one lot of V, and V dot I've got minus K over M U's and minus B over M V's. Okay, so here's the matrix A for my for the linear system in this form. Where should we go now? Okay, so I like this form because to understand the linear system, we study the matrix A. In particular, we look at eigenvalues and eigenvectors. So I'm hoping this should be familiar to you. Okay, so if V is an eigenvector and lambda is a corresponding eigenvalue, I apologize, I've got two different V's now. So now V is an n-dimensional eigenvector. So then e to the lambda t V is a solution to the linear system. Is a solution. And what is that? Well, it is a solution because I can just plug it into the differential equation and check that it works. So if I differentiate respect to t, I just get a lambda coming down. I can swap the lambda and the exponential because they're just numbers. So I've got lambda times v is a v. A v. And so sure enough, I've got A times my claimed solution X. Okay, so if we've got one eigenvector and one eigenvalue, that gives us one solution. So the idea is to get all the eigenvalues and all the eigenvectors, and that will give us the general solution. Lambda 1, lambda n. Okay, so an n by n matrix always has n eigenvalues as long as I'm counting multiplicity. Okay. It might not have n eigenvectors, but let's suppose for the moment that it does. And eigenvectors v n. So then well, then for each eigenvector and corresponding eigenvalue, this is one solution. But what's really nice about linear systems is I can add two solutions together. I get another solution. I can multiply a solution by a scalar and get another solution. So here the C1 to the Cn are just numbers. And so this is also a solution. Is a solution for all values of C. So for C1 n. And in fact, it's the most general solution. So any solution to this linear system can be written in this form, assuming it has n eigenvectors. How am I doing for time? Okay, so next I want to talk about the equilibrium. So in general, an equilibrium of a system of ODEs is a point where x dot is 0. So for the linear system, the origin is an equilibrium. So here's how I'm writing the origin. It's that the 0 vector is an equilibrium. And then we can look at subspaces of the equilibrium. So if I just look at the eigenvalues with negative real part, that these will correspond to exponentials that decay, and so those will correspond to solutions that go into the origin. So I could look at the set of all those solutions. That's an invariant subspace, and we call it the stable subspace of the origin. So it's the invariant manifold corresponding to all eigenvalues of negative real part. And with real part negative. So this fellow we call the stable subspace. We could also take all the eigenvalues with positive real part. That gives us the unstable subspace. It's some multi-dimensional. Oh, I'm just going outwards now. It's some multi-dimensional plane. Like, here we do U for unstable. And real part of land is positive. You could also have eigenvalues with zero real part, and that would give you a center subspace. I won't write that on the board. If your eigenvalues are complex, then your eigenvectors will also be complex. And you can still write the solution in this way, but it's usually nicer to instead use the real and imaginary parts of your eigenvectors in your solution. Just means that your solution doesn't have any complex numbers in there. And then finally, if you don't have n eigenvectors, if your system doesn't have enough eigenvectors, it turns out that there always exist n generalized eigenvectors. And you can use these so-called generalized eigenvectors to do kind of the same thing. Sorry, it's a bit of a mess there. I'll figure I'll just try and stay to the left of the screen there, just to be consistent. I can see I've got more room over there. Just want to say a little bit about two-dimensional linear systems, because lots of the examples of piecewise-smooth systems we'll get to later on will be two-dimensional. So in 2 dimensions, we can write our matrix A like this, and to understand the solutions, we want to look at the eigenvalues and eigenvectors. That the eigenvalues are characterized by the trace and determinant of this matrix. So that the trace of a square matrix is the sum of the elements on the main diagonal. Determinant, you of course know. And then, but we can use the values of the trace and determinant to classify the eigenvalues and the nature of really the nature of the origin is what we're classifying. And there are 5 cases. So that this curve is, delta is tau squared over 4. Okay, so first of all, if the determinant is negative, then you must have one negative eigenvalue, one positive eigenvalue. Imaginary. So in the complex plane, here's what your eigenvalues might look like. In this case, we classify the origin as a saddle. So you've got one negative eigenvalue, solutions going in, one positive eigenvalue, solutions going out. You could draw a little phase portrait if you like. X1, X2. I don't know what the eigenvectors are. They're just some eigenvectors, and one of them going in, one of them's going out. So that's subtle. And just quickly, the other four cases, let's see. Here the trace is positive and determinant is relatively small. So we've got unstable node. Here we have an unstable focus. So here your eigenvalues are complex. The real part is positive, so it's unstable. So it's unstable, solutions are going out, and the spiraling, so we call it a focus. Okay, so when you're dealing with nonlinear systems, as long as it's just two-dimensional systems, that this is a very good picture to have kind of ingrained in your mind for understanding equilibria. You can classify them just from the trace and determinant, as we'll see. Yeah, so for our mass on the spring here, what do we have? The trace is minus b over m. Determinant is k over m. But we'll assume that all the parameters that are positive, so m, b, and k are positive numbers. Then the trace is negative, the determinant is positive. So you're either in one of these two cases. If the damping coefficient is not too big, then you'll have a stable focus. So for a stable focus in the phase plane, your solutions will spiral in. But then if you look at a time series, so if you put time on one axis and x1 on the other axis, then you'll get some damped oscillations. So this is the underdamped oscillator, whereas over here it'll be overdamped. You won't have any oscillations. The solution will just decay exponentially. Okay, so I think that's enough about linear systems. Please stop me with questions if you have any. Okay, so this is an n-dimensional nonlinear system. Nonlinear. Okay, so if f is a function from Rn to Rn, and what we'll do is we'll Taylor expand the function f about some point. I'll call my point x star. So this is, of course, an autonomous system. The function f is independent of t. What else? I'm assuming that f is smooth. Plus e x minus Okay, so here's just our usual Taylor expansion that you learnt in undergraduate calculus very early on. So here, if is a vector valued function, f goes from Rn to Rn. So the constant term, I just evaluate f x star. A df is the Jacobian matrix. Should we try green? Again. And then I could include more terms if I wanted to. So next I'd have, well, the next term's kind of horrible because it's you have this order 3 tensor, but we don't need to worry about that. Okay, so if x star is an equilibrium, then this is 0. So this equals 0 if x star is an equilibrium. I mean, you could do the Taylor expansion. I've just done it. Even if x star is not an equilibrium, it's just not very helpful because orbits kind of move away just immediately, and it becomes unhelpful. Okay, so if x star is an equilibrium, this is just 0, and so what I'll do is truncate to leading order. So I'll throw away the higher order terms. Truncate. So constant term 0, I've thrown away the higher order terms. And so here's what I get. That this is a linear system. Let y so to put it in the form that I had at the start, I'll need to do a change of variables. So y is x minus x star. And then y dot will just be that the matrix times y. So I could call my Jacobian matrix A. And then I've got the form of the linear system I had at the start, except y instead of x. Is the microphone still okay? It's sliding up on me. Okay, so the purpose of this is that this represents an approximation to the dynamics of the nonlinear system which you're interested in. And as an approximation, it's sort of only useful near x star. And then the question is, how good is this approximation? And so for that, we have the Hartman-Grobman theorem. So I'm going to go back to the slides. My computer's fallen asleep because I spent so long on the blackboard. Yeah, so we consider arbitrary nonlinear system, where we just need f to be have a continuous derivatives so that the Jacobian matrix is well defined. We just need one more definition. We say that an equilibrium is hyperbolic if the Jacobian evaluated at x star has no eigenvalues with 0 real part. And then the Hartman-Grobman theorem tells us if x star is a hyperbolic equilibrium, then the nonlinear system is conjugate to the linearization. So the linearization is, yeah, here's the linearization. So it says that the nonlinear system is conjugate to the linearization. And what do I mean by conjugate? I mean that it is essentially the same as nearby, I guess. Conjugate means that the orbits of one system are mapped to the other system by a nice homeomorphism. am I doing for time? Okay, so next we'll just have one quick example where we can sort of see how the Hartman-Grobman theorem is useful. Perhaps I'll try over here since I've run out of space over there, for example. Next dot, please. Okay, so here I'm writing the vector x as the first component is x and the second component is y. So the example I've chosen is actually a Locker-Volterra predator-prey model. Volterra predator-prey. Predator-prey. So you've probably seen systems like this before in your undergraduate studies. So here x represents the prey and y is the predator. So in this very basic model, that the prey is assumed to grow at a rate 2, and the predator dies off at a rate 3. It dies off, hence the minus sign. But we also assume that the predators consume the prey, and the rate at which they do that is proportional to the number of intersections, or the number of interactions between the prey and predator. That the number of interactions is assumed to be proportional to x times y. So we've got a minus x times y for the prey and a plus x times y for the predator. But rather than go straight to equilibria, we'll look at the null clines because these are very useful. So the x null cline, it's where x dot is 0. X dot is 0. Okay, so I can set this equal to 0 and solve. So I get 0 is So I set this equal. I can factor out an x, and so I get either x is 0 or y is 2. And then in the same way, the y null cline is where y dot is 0. Right, 0 is y. Okay, so here I get y is 0 or x is 3. So the null clines are very useful if we want to sketch a phase portrait. X, y. So my phase portrait has x and y. Got an x null cline is where x is 0. So x is 0 is here. Or y is 2. It's 2. And then the y null clines where y is 0 or x is 3. And from this we can see equilibria, at least if I draw them in different colors perhaps. So anywhere where an x null line intersects a y null line, that's an equilibrium. It's where both x is 0, x dot is 0, and y dot is 0. Intersection. X null line. So an intersection of an x null line and a y null line is an equilibrium. So I've got x is 0. Should have done different colors. Intersects y is 0. So there's one equilibrium. And I've also got an equilibrium out here. Y is 2 and x is 3. But where the two x null lines intersect, that's of course not an equilibrium, because here I don't have y dot 0. Okay, so I got two equilibria. And so we can use the Hartman-Grobman theorem to, and also the analysis of the two-dimensional linear systems. Should be able to use those to classify these equilibria. Okay, so we'll need the Jacobian matrix. Okay, so first of all, we differentiate with respect to x. So differentiate with respect to x, get 2 minus y, and then differentiate with respect to y. And then on to y dot, differentiate with respect to x, and differentiate with respect to y, x minus 3. Good. And we want to evaluate the Jacobian at the equilibria. So let's start off with 0, 0. So here's the Jacobian. The trace is minus 1, and the determinant is minus 6. Okay, so you could also see that the eigenvalues are just 2 and minus 3. It's just a diagonal matrix. So I've got no eigenvalues with 0 real part. So therefore, the Hartman-Grobman theorem applies. Hartman-Grobman theorem. The Hartman-Grobman theorem applies for this equilibrium. So therefore, so the dynamics of the system near 0, 0, it's conjugate to the linearization. And for the linearization, we have a delta is negative. Delta is negative means a saddle. Yeah. Three, two, same sort of thing for the second equilibrium. X is 3, y is 2, 0, 3. Yeah, so now my trace is 0, my determinant is 6. Trace is 0, determinant is positive. That puts me on the positive delta axis. My eigenvalues are purely imaginary, and it is plus minus so my eigenvalues have 0 real part. So for this equilibrium, the Hartman-Grobman theorem does not apply. Yeah, so that's perhaps unfortunate. So with this as a linear system, if I've got, for a linear system with purely imaginary eigenvalues, that's called a center, and the orbits are loops. the nearby orbits are closed loops. But for a nonlinear system such as this, it's conceivable that orbits could instead converge to the equilibrium, or they could spiral outwards. It turns out that for this system, orbits are actually closed loops. So which way around do we go? This way. So for this system, orbits are closed loops. I don't know that's a Hamiltonian system, but certainly you can do an additional calculation to prove that orbits follow closed loops. Just want to draw a few more orbits. So once we've got the null clines, so for each region bounded by the null clines, the orbits follow kind of a basic direction. So for example, if I'm in this region, for example, x is 1, y is 1, x is 1, y is 1, x dot is positive, and y dot is negative. So throughout here, orbits go down and to the right. As I cross over the y null cline, orbits start to go up. And then I cross over the x null cline, orbits go to the left. And then back across the y null cline, orbits go down again. So I can use that to help me draw a reasonably accurate phase portrait. I guess so let's turn there, and then I turn here, and then there. Back again. And as we saw earlier, the origin is a saddle. That way. And so. So I should say that for most of, I think for all of my lectures, except this one, it's a 90-minute lecture, which is a long time for you to concentrate. So for my other lectures, I have sort of an exercise for you to do sort of in the middle of the lecture. Today, instead, I've got a movie at the end. So if you make your way to the end and there'll be a movie, yes. Yes, so I didn't write that on the board. So conjugate, essentially it means that the two systems are the same. That's right, yes. So this is a completely different use of the word conjugate. So, it's a different use of the word conjugate. It means that there exists a homomorphism between the nonlinear system and the linear one, such that the homomorphism maps orbits of one system to orbits of the other system. For this example, oh yes, no limit cycle, that's right. You've got uncountably many periodic orbits, but no isolated periodic orbit. It's a limit cycle is an isolated periodic orbit. Thank you. Any other questions before we move on? Yes. Well, we can't in this case. So we can't apply the Hartman-Grobman theorem to this case. So from the calculations on the board, we don't know that orbits really do go in loops. you have to do an additional calculation to show that, which is it's a bit tricky. You have to eliminate time from the equations to get just y as a function of x. Yeah. Okay, so now we'll suppose that our system of differential equations, it depends on a parameter mu. And for simplicity, we'll take mu to be a real number. And so as we vary the value of mu, you can imagine how the phase portrait changes. So typically, equilibria kind of move a little bit, and limit cycles move a little bit. Eigenvalues change a little bit. So usually, as you vary the value of mu by a little bit, qualitatively nothing much happens. And this is a good thing. So if your equations represent some mathematical model of some physical system, that the parameters in your model will be usually experimentally measured. So it's nice to know that for some acceptable range of parameter values, that the qualitative dynamics is pretty much the same. However, there'll be special values of mu at which the dynamics changes sort of in a fundamental way. And so these values are called bifurcations. Okay, so I don't want to say what I mean by changes in a fundamental way. I just want to go through a couple of examples. Find my notes. Yeah, so we'll start off with this one-dimensional example. So x dot is okay, so equilibria satisfied x dot 0. This will be equal. So this is the equation we need to solve to find equilibria. And unfortunately, we can't solve for x without using the formula for the roots of a cubic, which is really quite horrible. You never want to use the formula for roots of a cubic. Instead, we could solve for mu instead. So mu equals, and then I'll have it implicitly. So I'll have the equilibria given implicitly in terms of mu. That's all. I'll call the equilibria x star, so x star minus x star plus star cubed. And then we can use this to plot. I can use this to plot the equilibria as a function of mu. So this is the picture I want. I want to plot the equilibria as a function of mu, but instead I've got mu as a function of x star. So I just plot my cubic kind of sideways. Okay, so there it is. So. Yeah, right. I'll just use the board, I guess. I'll use the screen. So as we vary the value of mu, say from the left to the right, so here I've got, we just have one equilibrium. Here we've got three equilibria, and then over here we've got one equilibrium again. So as we increase the value of mu, as we cross this special value, a little bit more than minus 0.5. Across this value, that the number of equilibria changes from 1 to 3. And that's a fundamental change in the dynamics. So this is an example of a bifurcation. It's what we call a saddle node bifurcation. And there's a second saddle node bifurcation here, where the number of equilibria goes from 3 back to 1. So this value is minus 2 over 3 root 3. You can do the calculus to get that number, and it's symmetric, so the same, or the negative over here. Yeah, so these are saddle node bifurcations. So saddle node bifurcations are where you have two equilibria collide and annihilate, or depending on your point of view, you've got two equilibria appear out of nowhere. So exactly at the bifurcation, you've got one equilibrium. This equilibrium will have a zero eigenvalue. In fact, as you follow the curve along, the eigenvalue will change. It will pass through 0. So for this example, I've got here we have a negative eigenvalue, and then we go to a positive eigenvalue. So the equilibrium changes from being stable to unstable. Or really, we've got two equilibria, a stable one and an unstable one, and they collide and annihilate. Well, I mean, we've also got our other equilibrium up here. That this equilibrium doesn't influence the saddle node bifurcation. Saddle node bifurcation is a local phenomenon, just affects what's happening in the neighborhood of a point. So the fact that we've got some other stuff happening up here is not important. Yeah. I should say, you probably know already, that this type of bifurcation is called a bifurcation diagram. Bifurcation diagram. So for a bifurcation diagram, you've got a parameter on the horizontal axis and a variable on the vertical axis. And you'll see lots of bifurcation diagrams as we go along, and presumably you've seen some already in the last 3 days. Okay. Oh yes. I suppose, no, that's right. There's certainly no other equilibria, and it's just a one-dimensional system, so you can't have limit cycles or anything else. Really, equilibria are the only invariant sets. So I think this picture summarizes all the dynamics that the system has. Okay, another example, here we've got a two-dimensional system. This is called the extended van der Pol system. It was studied in a paper by Koper from 1995. Yeah, so it's two-dimensional. You've got variables x and y, and you've got a bunch of parameters a0, a1, b1, b2, and epsilon. And so I'll just quickly show a few bifurcation diagrams that are in this paper. So what he's done, he's got 5 parameters. He's fixed 4 of them at some nice values, and then he's just varying the last one. So he's varying a0. So he's got a0 on the horizontal axis and x on the vertical axis. He's got 6 different pictures because he's he's got 6 different choices for his other 4 parameters. So perhaps we could just look at the first bifurcation diagram, the one on the top left. Let's see if we can make sense of what's going on there. What should we do? Perhaps I'll draw some representative phase portraits. So X and a Y. I want to do several different values of A0. So we'll start off with the value of A0. It's kind of small. Perhaps I'll sketch the bifurcation diagram. A0. And what's he got on the vertical axis? X. That's sensible. And then. Oh, sure. So there are the equations again. Okay, so I'll start off with a value of A0 on the very left. So here we just have one equilibrium. I don't know where it is. I don't know. One equilibrium somewhere. That the solid line means that the equilibrium is stable, whereas the dashed line means it's unstable. So here we've got a stable equilibrium. I don't know what the eigenvalues are, so I don't know if it's a focus or a node, but either or, it's stable. And then as I increase the value of A0, X and Y, next. Okay, so now I've crossed a saddle node bifurcation. So now I've got 2 extra equilibria. So this one stays pretty much the same. In fact, this one's for a large value of X. This one should be quite large. And then I've got 2 at smaller values of X. One's stable, one's unstable. So stable. So I would presume that the phase portrait looks something like this. I've got 2 stable equilibria, 1 unstable equilibrium. That this equilibrium must be a saddle. So I have to have 1 stable direction, 1 unstable direction. The reason it must be a saddle is because this one's stable, and as I go through the saddle node bifurcation, I just have 1 eigenvalue going from negative to positive. Okay, and then next, just increase A0 some more. So this is a saddle node bifurcation. The next one is labeled H. This is a hop bifurcation. So at a hop bifurcation, the stable equilibrium loses stability by having the real part of a complex conjugate pair of eigenvalues, that the real part changes from negative to positive. And you get a limit cycle is created around the equilibrium. So now, can I draw that? Oops. Y. So my equilibrium, it's changed to a focus, and then the focus goes stable focus to unstable focus, and now it's unstable. And I've got a stable limit cycle. And then I've still got my other two equilibria. In, and this one has to curve to that way, I guess. Oh, it's a stable limit cycle, so that's going in. Cool. And then what happens next? So if I increase A0 some more, then I hit this other saddle node bifurcation. So the next thing is that these two equilibria will collide and annihilate. And I'll just get left with the unstable equilibrium and limit cycle, stable limit cycle. And then if I keep increasing A0 some more, I get to another Hopf bifurcation. This time it goes backwards, so the limit cycle collapses down onto the equilibrium. And the equilibrium goes back from being an unstable focus to a stable focus. So that's roughly what the phase portrait will look like at the end. So I won't go through the other ones in detail. Perhaps we could just look. So the next one, you've got this SL. So what happens is you've got your saddle node and your Hopf bifurcations in the same way. Saddle node and then Hopf somewhere. You get a stable limit cycle being created. And then what happens for the top right bifurcation diagram is that the limit cycle, it collides with the unstable equilibrium, and the limit cycle gets destroyed. So, yeah. Explore. Unstable equilibrium. That can be trying to draw it fairly consistently. There we go. It's going in and that's going out. That's going out, and it's a bit turned around now. So we have our limit cycle. The limit cycle grows until it hits the equilibrium. So exactly at the bifurcation. Exactly at the bifurcation, you'll have an orbit that looks like this. This is a homoclinic orbit. This is called a homoclinic bifurcation. Here he's labeled SL. Why did he do that? SL. Super. SL. Don't know where the abbreviation SL comes from. Yeah, and then you have another homoclinic bifurcation, and the limit cycle reappears. You also have this one you notice called sniper, which sounds very exciting. A sniper bifurcation is just a saddle node bifurcation, but you also have a limit cycle created at the same time, just due to global properties of the system. I think that's about all I need to say. So the important one is the Hopf bifurcation. plus or minus I omega. So at a Hopf bifurcation, your equilibrium has purely imaginary eigenvalues. You get a limit cycle being created. The limit cycle grows at a rate proportional to the square root of the parameter change. So I should have said, so what I'm actually plotting in the bifurcation diagram here, I'm plotting the maximum and minimum x values of the limit cycle. And so this curve is roughly a parabola sideways. So the amplitude of the limit cycle grows like the square root of the parameter change. But in this case, you get a stable limit cycle being created. You could also have an unstable limit cycle being created instead. It would have to go to the left in that case. So either a stable limit cycle or an unstable limit cycle. It depends on higher order terms in the system. Right. I lost my point. Okay, so just one more thing for this lecture that I wanted to do. This guy. So I have a movie to show you, so hopefully it works okay. I'll just not touch it. Okay, so yeah. There's no sound with the video. Yeah, so this is the Tacoma Narrows Bridge. It was built in the late 1930s in Washington State in the US. It opened in July 1940. It was a new type of suspension bridge. It's designed to flex a little bit in high wind. Unfortunately, it was found to flex a lot in relatively low wind. As you can see, it's quite a compelling video. You've got these bridges flexing an incredible amount in just quite a low wind. It eventually collapsed just about 3 months after it opened. So it was long thought that the large oscillations that you're seeing here were caused by resonance, which seems like the obvious cause. Nowadays, it's believed to be due to more complicated nonlinear dynamics, combining the fluid dynamics of the air, of the wind going past, and also the mechanical dynamics of the bridge. I'll just let the rest of the movie play out. There's a very brave man. That's it. Okay, so what I wanted to show you today is just an extremely simplified ODE model that gives us some kind of inkling into how the dynamics, how the nonlinear dynamics can play a role. Right, and so here, this is the mathematical model formulated by Laser and McKenna, and it's a ridiculously simple model. So it's on the left-hand side, you've just got your mass on a spring. So the mass is 1, damping coefficient is 0.01. The spring constant is a bit more complicated. I'll get to that in a moment. And then on the right-hand side, you have an applied force. So in particular, you've got harmonic forcing. Harmonic forcing is, what Evan says, harmonic forcing is due to swirls or eddies caused by the wind. So Y represents the vertical displacement of the center of the bridge. So Y of t is up and down, and Y equals 0 corresponds to where the cables are stretched. This Y equals 0 is where the cables are taut but not stretched. So for Y negative, the cables are stretched, holding the bridge up, whereas for Y positive, the cables are slack. They're all a bit bent. So that's why you've got this extra -10 there, just to make sure that usually the cables are stretched. Okay, so the one key feature of the model is that the spring constant K is assumed to have different values depending on where Y is negative and Y is positive. So I said today that I just do smooth systems. I guess I lied. I couldn't help myself. This is now a piecewise smooth system. So the spring constant is larger when the cables are stretched. So there's more force. Whereas when the cables are slack, which the cables are definitely not supposed to be slack, then you have a slightly smaller value. Okay. So let's think about solutions to this. Here we go. I can just write here, actually. So lambda is the one parameter in there. The full model has more parameters. I've just got the one parameter. Lambda represents the forcing amplitude. So with lambda equals 0, if lambda is 0, I can tell you what one solution is a solution. So we have an equilibrium, y equals -10/17. This equilibrium is a solution. It's also a stable solution. You could, because the damping coefficient is positive, you can just do the same kind of analysis we did at the start to get your 2x2 matrix. And you'll see it corresponds to a stable focus. So orbits spiral into this equilibrium. So if lambda is positive, but not ridiculously big, it needs to be less than 0.587 something or other. In this case, you have a stable periodic solution, and we can write the periodic solution exactly because we've just got nice harmonic forcing. You'd have solved an equation like this in undergraduate. So plus a, what a? Okay, so if lambda's in this range, then this is a solution. So I've got the equilibrium plus some sine function. So here A. Here A is not a matrix, sorry. A is just a number. A is the amplitude of my solution. In fact, we can calculate A. A is lambda over some number, 1.0016. So that the amplitude increases linearly with respect to lambda. We've also got some plus A that I'm not going to worry about. That's just change in the phase. It's just some number that's not important. what to talk about. So what does this solution look like? I think I've got room here. So t, so I want to plot it as a function of t, so y is a function of t. There's my stable equilibrium. So this solution is it's simply oscillations about the stable equilibrium. It's not very exciting. These oscillations are acceptable for the bridge. The designers intended the bridge to have a small amount of oscillations. What they didn't want to have happen is have large oscillations. But actually, that's what the model gives. And so this is the really interesting part. These are some time series I computed in MATLAB. So I just put lambda as 0.1. So my amplitude is quite small. It corresponds to quite moderate winds. And here's the solution I just wrote on the board. It's a stable solution. But what's fascinating is that it's not the only stable solution. You have large amplitude oscillations that they're not exactly stable. You can see the amplitude, it sort of goes y is positive here, but then it sort of dips down to y negative. But if you keep following it, if you keep following this, it goes back up again to y positive. I don't know if it's quasi-periodic or weakly chaotic even. So the point is that you get coexisting solutions. You get two different attracting solutions, an acceptable small amplitude oscillations, and you also get these disastrous large amplitude oscillations. And the reason you get this, the reason you have coexisting solutions is because your model is non-linear. If k was a constant, it's just a linear system with harmonic forcing. That's really all it can do. By making it non-linear, in fact, piecewise smooth, and you get some more complicated behavior that could possibly explain what happened to the bridge. Okay, so that's all I wanted to get to in this lecture. Sorry, it's a lot of me talking. So for my other 5 lectures, we'll have a little break in the middle, and I'll give you an exercise to work on. But we'll leave it there for right now. That's okay. Any more questions? Please feel free to ask. Well, k is a function. So here's my function of k. What is the value of k? Well, k is piecewise constant. So for y negative, k is 15, k is 17. For y positive, k is 13. So these two pictures are for the same parameter values. All I've done is I've chosen 2 different initial conditions. That's all I've done differently.